So in this next video, we're going to look at the third problem from the Chapter 3, Part 2 homework. We have some sort of, looks like a gear shaft. It is hinged at point B. We have the handle or a point at which we apply forces at point A. And what we're interested in is basically what's the smallest amount we can push it at point A in order to exert a certain moment or torque or a tendency of rotation about point B. So this is a pretty common problem or kind of principle that we've looked at quite a bit up until now, which is if we want to minimize the amount of force that we have to apply, we want to direct that force perpendicular from an actual position vector that's drawn from the point about which we're trying to induce rotation, which is going to be the point that it's pinned, point B, to the actual point of application. So what we want to do is make sure that this is applied perpendicular to a line that goes from B to A. So how would we actually go about determining what the geometry of that line is and so on? So what you probably want to do initially is actually draw a triangle that goes from point B to point A and actually make it a right triangle because we're given the geometry that the horizontal displacement from B to A is 8 inches and the vertical displacement from kind of the base or point B to A is 22 inches. So we notice that any actual geometry defined by that triangle is going to have an interior angle that is defined here from the actual position vector to the vertical displacement as the inverse tangent of opposite over adjacent side length, or 8 divided by 22, which is going to be about 19.98 degrees. So that's just to say that that position vector is kind of declined from the vertical by 19.98 degrees. Now, the next thing, when you know the local geometry of the position vector from the point that you want to compute the moment about B to the point of the application of the force, is to try to determine what the relationship is from the actual to the geometry of the force that you're applying. So the key point being here, I just drew the easiest way that is for me to see is to draw a traditional vertical and horizontal coordinate system. And then note that the actual position vector from B to A is defined by this angle theta. So if you want to have a line that's perpendicular to that, I kind of view this as a rotation of your traditional coordinate system. So if the actual position vector is rotated at theta, in order to stay perpendicular, the point of application of the force needs to be theta degrees elevated from kind of the horizontal axis. Well, if you look back at the original problem, that is the geometry that defines alpha, is the elevation of this force from the horizontal axis. So in order to make it perpendicular to the actual line of action from B to A, that angle alpha actually has to be theta. So that's the first thing that's a little bit hard to see. So you know the direction that the force has to be applied just based upon the geometry of this situation. Now, the second question that you need to determine is, okay, now that we know the angle of application, well, what's the perpendicular distance? So the perpendicular distance is just going to be the distance from B to A, which you can get by Pythagorean theorem. Again, with a right triangle, this is nowhere near to scale, where the space is 8 and this height is 22. So you can use Pythagorean theorem and determine what that distance is. And once you know that distance for whatever amount of torque or moment you're trying to actually exert, you know that that magnitude is equal to the product of that distance times the force that you're applying. So knowing that distance, if you have a minimum amount of magnitude of moment that you're trying to exert, just divide that by the distance and that will give you the magnitude of the force. And you know that it has to be applied at an angle alpha equal to theta, which is defined by the geometry that we did at the beginning of the problem.